Okay, let's take a look at a few examples of solving quadratic equations. Recall, a quadratic equation is an equation that can be written in this form for some constants a, b, and c, as long as a is not 0. Of course, if a is 0, this term isn't really here, and we're left with a linear equation, or a first-degree equation. All right, so what do we do when we encounter a quadratic equation? Well, it depends on what it looks like. Example 1. Suppose we have 4x squared minus 3 equals 0. Now, one really nice thing about this particular quadratic equation is there is only one occurrence of x. Okay? When that happens, things are pretty easy, right? We can just apply the socks and shoes principle. Think about what happens to x in the evaluation of this expression. First you square it, then you multiply by 4, then you subtract 3. The last thing was the subtraction of 3. To undo that, we could add 3. So let's add 3 to both sides. We get 4x squared equals 3. Then, again, looking at this, first we're squaring x, then we're multiplying that result by 4. The last thing that happens was multiplication by 4. So let's undo that. Let's divide both sides by 4. That's going to give us x squared equals 3 over 4. Now at this point, there's not a single function here I can apply to undo the squaring on x, but I know if something squared equals this thing over here, then x must be either the positive or negative square root of this thing on the right. So x is going to be either positive or negative of the square root of 3/4. Of course, let's keep things nice and simple here. The square root of 4 is 2, so that's plus or minus the square root of 3 over 2. Okay? That's one way you can proceed. Another way you could have gone is to realize, hey, this is a difference of, well, let's see, this is a perfect square. Is 3 a perfect square? Well, it's not a square of a nice integer number, but it is the square of the square root of 3. We could, I suppose, factor this into 2x plus the square root of 3 times 2x minus the square root of 3, right? It is technically a difference of squares as long as we're okay with the fact that 3 is the square of the square root of 3, which of course it is. Now you have a product equaling 0. This is incredibly important because this tells us one of those two factors itself must be 0. If they're both non-zero, then this can't possibly be 0. Okay, so that tells us either 2x plus the square root of 3 equals 0 or 2x minus the square root of 3 equals 0. This is great because we have reduced the difficulty of our problem. It used to be a quadratic equation. Now we have two linear equations, and they're solved in the normal way. Isolate the x. Get rid of the square root of 3 by subtracting it from both sides. So that's 2x equals negative square root of 3. Over here we have a negative square root of 3. We want to get rid of it by adding square root of 3 to both sides. 2x equals positive square root of 3. In both cases we got to get rid of the 2 next. So we divide both sides by 2. So here we get x equals negative root 3 over 2. Or again, x equals positive root 3 over 2. That's identical to what we got here. Okay, so that's another way we could go. This, I think, is a little bit easier, of course, in this case. But let's consider example number 2. X squared minus x equals x plus 3. Here we have multiple occurrences of x in our equation. Okay, remember that first method we used on the first problem required only one occurrence of x. Now, I suppose we could reduce the number of x's we see here by pulling everything to one side. So, for example, I could subtract x plus 3 from both sides. That's going to give me x squared minus this x minus the x we just subtracted, so that's minus 2x. And then minus that 3 equals, and of course if I subtract x plus 3 from the right-hand side, I get 0. But I still have two x's, and there's no convenient, nice, quick, one-step technique for collecting those two together because we have different powers. Now we can take a cue from the second way we solved our first problem. We have something equaling 0. If we're fortunate enough to be able to write this thing as a product equaling 0, then one of those two factors would themselves have to be 0. And given that if we can write this as a product of two things like this, those things are likely to be linear, then we will have made our problem a little bit easier. Let's see if it plays out. So if I assume these two things are binomials, which seems reasonable since that's a trinomial, x and x here and here would probably be pretty reasonable choices since that has to be x squared. The product has to be x squared. The last two terms, remember, have to multiply together to give us -3. So let's put the number parts in there, the magnitudes in there, 3 and 1. When it comes to picking the signs, this tells me one's positive, one's negative, but I don't know which order. But I do know that if I look at the inner product and the outer product, that it has to sum to give me -2x. And that can only happen if we make the 3 negative and the 1 positive. So I've factored this thing, and now I know, because the product equals 0, that either this factor or this factor has to be 0. And I have two cases. Either x minus 3 equals 0 or x plus 1 equals 0. Notice how much simpler those two equations are compared to one of these two original equations. Here, of course, add 3 to both sides and you have x equals 3. Or, in this case, subtract 1 from both sides and you have x equals -1. And that is your solution. Okay, so we were able to solve this quadratic by factoring and then setting each factor equal to 0 and solving. And it hinges on the fact that you have a 0 right there. Okay? If you see a trinomial here equals 7, don't factor the left-hand side. Move the 7 back over there first before you factor, because if you don't have a 0 here, you can't apply this special principle that says if you have a product equaling 0, one of the two factors equals 0. Okay? All right, let's look at another example. X squared plus 4 equals 0. Okay, there's our 0. That's great. We could try factoring this, but hey, look, it's a sum of two squares. And generally that does not factor, at least not into polynomials with real coefficients. Okay, it cannot be factored. We could try the technique of, hey, look, I've only got a single occurrence of x. Isolate it. Get rid of the things that are happening to it. First you square it, then you're adding 4, so we got to get rid of the 4 first. Subtract 4 from both sides will do it. That's going to leave us x squared equals -4. But then we've got a serious problem, don't we? Can anything squared give us -4? When you square something, you get 0 or a positive value. That never happens. Okay? So there are no solutions to this particular quadratic equation. Okay? Okay, example number 4. 2x squared minus 3x minus 2 equals 1. Okay? Now here again, we've got a trinomial. We can't collect our x's together because we have different powers there. We have a 1 on the right-hand side. Okay? I'm going to go ahead and assume that maybe we'll get lucky here. And if I take this 1 to the left-hand side by subtracting 1 from both sides, so it becomes -3, and the right-hand side becomes 0. I do this under the assumption that maybe I'll get lucky if I have a 0 here, and if this factors, I can reduce it down to two linear equations. Okay, so if we try to factor this thing, let's see some reasonable choices for our first two terms, probably 2x and x, since their product has to give us 2x squared. For the last two terms, it looks like we need a 1 and a 3. It makes a difference, of course, whether I put it 1, 3 or 3, 1, because I get different inner and outer products as a result. Let's try 1, 3. Maybe we'll get lucky here. The inner product is a single x. The outer product is 6x. Can we get negative 3x from either adding or subtracting a single x and 6x? I don't think so. So let's go back and try the other way here. Let's see, how about 3 here and a 1 here? The inner product is 3x, the outer product is 2x. Can I take a 3x and a 2x and add them or subtract them together to get negative 3x? Uh-oh, that doesn't work either. In fact, you can't factor this nicely. Okay, so we need another method. Now, there is a clever trick we can pull here. I'm going to start from this. 2x squared minus 3x minus 3 equals 0. And you'll notice I left myself a little space here. Here's the trick. I want to reduce this down to an equation that only has one occurrence of x in it. To that end, let's first pull out this 2 as a factor from the first 2 only, the first 2 terms. So that's going to give us x squared minus 3 over 2x, right? 3 over 2, because 2 times that, the 2's cancel, and you get your 3 back. And then I'm going to put a closing paren with a little bit of space. I'm going to leave that minus 3 right where it was. Okay. Now my hope is, and again, I'm trying to turn this into an equation with a single occurrence of x. Okay, by the way, the technique we're employing here is called completing the square. And that's exactly what I'm going to do next. I'm going to insert something right here so that all of this is a perfect square, a square of a binomial. Now remember, what do squares of binomials look like? If you have a plus b squared, if we FOIL that out, right, we would get something like a squared plus 2ab plus b squared. So the first term is a perfect square. The second term is 2b times the a, right? 2b times the thing we squared to get this. And of course this is that b squared, whatever that happened to be. Let me write this slightly differently. If this was x plus b squared, we have x squared plus 2bx. I'm going to group that together, right? 2b times x plus b squared. Look at this form compared to what we have up here. X squared matches with the x squared. The x matches with the x. That means the negative 3 halves is our 2b. Negative 3 halves is our 2b. So the third term, b squared, if I just know what b was, I could figure out what that is, right? But we can figure out what b is. Look what we have here. All I've got to do is cut both sides by 2. Cut them both in half. I have to divide by 2. So this tells me that b is negative 3 over 4, right? Half of negative 3 halves is negative 3 fourths. So I take this coefficient right here, and I have it to get negative 3 fourths, but then the term I'm missing is the square of that. So I take this, I have it, that's negative 3 fourths, and then I square it to get 9/16. Okay, now we just inserted that number so that this would be a perfect square, but you can't take an equation and just insert a number. It's not the same equation, but we can insert a number and compensate for that insertion. By inserting this number, what did we actually do to the left-hand side of the equation? We actually added the product of 2 and 9/16. If you multiplied this all out, that's how it would look different, right? That extra product would be there. So what if we then we can compensate for that insertion in 2 ways. We could either subtract it right back off again, right here under the minus 3, we could say minus 2 times 9 over 16, or I could add it to the right hand side. Either way is fine. Let's add it to the right side in this case. So I'm going to add 2 times 9 over 16. Of course, 2 and 16 cancel. So I'm going to add 9 over 8. Okay, so I inserted what I wanted to see so that this was a perfect square, hence completing the square, and I compensated for that insertion. Again, I could have added 9/8 here, I could have subtracted 9/8 on the left. Either one is fine. Now what does this afford me? I can rewrite this as 2 times a perfect square, namely x minus 3/4. I still have a minus 3. I still have a 9/8. The 0 went away, of course. Notice what we have. An equation with only one occurrence of x in it. We're home free. Right? Look at the things that are happening to this x. You subtract something, you square something, you multiply by something, you subtract something. Let's undo those things in reverse order. The last thing that happened was the subtraction of 3. Let's add 3 to both sides. Let's see, 9/8 plus 3, that'd be the same as 9/8 plus 24/8, which is 33/8. So now you have this equals 33/8. In evaluating this expression, the last thing that happens is, let's see, we subtract off 3/4, then we square it, then we multiply by 2. It's the multiplication by 2. So let's divide both sides by 2 to undo that. So dividing by here, over here by 2, that's the same as multiplying by a half. So that's like, let's see, times a half there, that'd be 33/16. The last thing that happens in the evaluation of the expression on the left this time is, let's see, we subtract 3/4 and then we square. So it's the squaring. To undo the squaring, remember we can't undo that uniquely, but we can say that x minus 3/4 must then either be the positive or the negative square root of 33/16. That's the positive or negative square root of 33/4, because the square root of 16 is 4. And last but not least, x equals, by adding 3/4 to both sides, we can get rid of this. Nicely, they have common denominators already, so I can say this is 3 plus or minus the square root of 33/4. And we have our answer. Okay, again, that's a technique called completing the square. It turns out we can use this completing the square in other contexts too later in calculus, so it's really, really important that we remember it. What do? We isolated off the quadratic and linear terms from the constant term. We factored out the coefficient on the quadratic term. We gave ourselves a blank and figured out what this term should be, what we need to insert here, so that these 3 terms are a perfect square. And the way we did that was we took the linear term, halved it, and squared it, right? Negative 3/2 halved is negative 3/4, squared is 9/16. We insert that, but then don't forget to compensate for that insertion, either by subtracting off, not this, but the product of this and this from the left side, or as we did here, by adding it to the right side. Then you can rewrite it, expressing these 3 terms as a perfect square, and that's where you go from 2 occurrences of x down to a single occurrence of x. And from there, it's just that socks and shoes principle, right? Undoing the last thing done in the evaluation of the expression until you don't have anything being done to x, and you're back to your solution. Okay? So that's the completing the square technique for solving quadratic equations.